Hello, my name is Jonathan Sanders. I'm in a group with Caleb and Tim. Today we'll be speaking to you about rotation about a fixed axis. Now when speaking about rotation about a fixed axis, you can find this in your book in chapter 16.3. Now when referencing this, for rotation about a fixed axis, you need to know two things: a rigid body and the point of rotation. A rigid body is made up of a system of particles which stay at a fixed distance from one another and do not deform. An axis rotation is what it sounds like. You can only have one axis of rotation per rigid body, and to check if it's a fixed rotation about a fixed axis, follow a point over a period of time of the movement of the rigid body around the axis, and if it creates a circle, then you're dealing with rotation around a fixed axis. Some concepts we'll be looking at today will be angular and tangential acceleration, velocity, and kinematics. Now, Jarvie's going to come to the scene and demonstrate our design.
So basically in our presentation, we are solving for angular acceleration of the wheels at a fixed point. Now we use wheels because this will make it smoother and it won't catch on to anything. Now some variables that are given are the distance in which the object is dropped, the radius of the wheel, and the number of teeth on each of the gears for each wheel. Now during the experiment, there will be two times that will be recorded. The first time is the time in which it takes for the object to fall from a given point to the ground, and the second time is the time for the wheel to make one full revolution. Now after equating the variables and the time in the experiment, we are able to calculate for the tangential acceleration of the wheel due to gravity. By finding that, we are able to calculate the angular acceleration of the front wheel, which then, using the gear ratio and the chain, we are able to solve for the angular acceleration of the back wheel. After that basically accounts for the angular velocity, angular acceleration, and the motion of the wheel. Now I will give it over to Caleb, who will talk about the data and analysis of the project.
In this experimental setup, we're going to observe how the equations that we use to relate tangential and angular motion are related to each other. We're first going to create a tangential acceleration and measure that, and then we're going to work our way through a system of equations and calculate the angular momentum or angular acceleration of the back wheel. We're also going to time the time it takes for the back wheel to make one full revolution to calculate its angular acceleration that way. We will then compare those two angular accelerations to each other and find that they are actually very close. And that's what we expect from a rigid body rotating around a fixed axis. In fact, over a period of time that we took calculations, our average error was about 6.4%. Alright, now I'm going to run you through some actual calculations and show you the process by which we calculate the two different angular accelerations. First, let's start with the things that we know for sure. We know the height that the weight falls from, we know the radius of each wheel, and we know the number of teeth on the first gear and the number of teeth on the second gear. Now we can look at the two values that we measure. The first one is the time that it takes for the weight to fall from rest over the known height. The second time is the time it takes for the back wheel to make one full revolution after having started at rest. The first calculation that we're going to look at is the calculation we use to calculate the tangential acceleration of the weight that's fallen. We're going to use the equation x equals x naught plus v naught t plus 1/2 at squared. But we know, since it starts at rest, that v naught is 0, and we're going to set x naught to 0 at that point as well, which boils the equation down to x is equal to 1/2 at squared. We solve for a and get 2x over t squared. We can solve for A, and we get the value 0.473 meters per second squared. Using that acceleration, we can calculate the tangential velocity using the equation v equals v naught plus at, where v naught is equal to 0, and we can calculate the position using the equation x equals x naught plus v naught t plus 1/2 at squared, knowing that x naught and v naught are both 0. This way we can calculate the velocity and the position at any point in time. The second equation that we're going to use is alpha r is equal to tangential acceleration. What we're going to do here is we're going to calculate the angular acceleration of the first wheel by relating it to the tangential acceleration of the weight, which was coming off of the rope wrapped around that first wheel. If you solve the equation alpha r equals at, we get the equation alpha is equal to tangential acceleration over r. And the value we get for alpha is 1.66 radians per second squared. Using the equation omega equals omega naught plus alpha t, where omega naught is 0, we can calculate omega for any point in time. And using the equation theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared, where theta naught and omega naught are both 0 as well, we can calculate the angular position at any point in time based on this angular acceleration. The third calculation we're going to run through is the equation we use to translate the first angular acceleration to the second angular acceleration using the gears. Here you can see a picture demonstration of the chain and the gears. Since the chain always has a constant acceleration, that means that the tangential acceleration at the edge of each of the gears has to be the same. Using the equation alpha r equals tangential acceleration, since the tangential accelerations are equal for both, we can write the equation alpha 1 r1 is equal to alpha 2 r2. We can solve that equation for alpha 2, saying alpha 2 is equal to alpha 1 r1 over r2. Since we're using gears with teeth and a chain instead of normal gears that rotate right next to each other, it's more accurate to use the number of teeth on each gear. So the equation we're actually going to use is alpha 2 is equal to alpha 1 multiplied by the number of teeth on the first gear over the number of teeth on the second gear. The value we get for that is 4.22 radians per second squared. The fourth equation we're going to use is used to calculate the angular acceleration based on the time. We use this to check our calculations to see if they match up. We use the equations theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared, where we know that omega naught is 0 since it started at rest, and we set theta naught equal to 0. We can solve for theta, saying theta is equal to 1/2 alpha t squared, and then solve for alpha, saying that alpha is equal to 2 theta over t squared. Theta in this equation is going to be equal to 2 pi, since that is the number of radians in one full revolution. We solve alpha to be 3.97 radians per second. If you compare that angular acceleration with this angular acceleration, you can see that they are remarkably close. We can calculate the error by subtracting the angular acceleration measured from the angular acceleration calculated and dividing that by the angular acceleration calculated. We multiply that by 100 to get 6.12% error.
Now that we've gone over the equations and how the system works, we will do a quick demonstration of what will happen. Caleb over here will be timing the time it takes for the object to reach the ground, and John over here will be timing the time for the back wheel to make one full revolution. We will use those times then to plug into the equations that we did before.
1, 2, 3.
We hope you learned more about rotation about a fixed axis today, as well as you can find this in the real world. Many instances would be gears with an engine, since all of these are rotations about fixed axes, and you can find the relation between tangential and angular accelerations and velocities. We also hope you learn more about the concepts surrounding the idea of rotation about fixed axis, these being the kinematics and angular acceleration and velocity equations. Thank you.